Hi, and welcome to our PADT webinar series about the Stratasys Origin Two DLP printer. PADT is Phoenix Analysis and Design Technologies. We're an engineering, design, analysis, and manufacturing company based in Tempe, Arizona, and we are a Stratasys technology reseller. I'm Pam Waterman, Senior Application Engineer for 3D printing. In the previous 4 webinars, we presented in recent weeks about the Origin Two system. We've covered materials, printer functions, applications, and software. Now, in this final webinar of the series, we bring it all together and look at the total cost per part or return on investment for 3 different part geometries, meaning should you or shouldn't you 3D print these parts given the full workflow and cost analysis of owning an Origin Two system. To start with, what goes into figuring out the return on investment, or ROI, of operating an Origin Two DLP resin printer? It depends a great deal on part geometry, as well as on such factors as material amount, material cost, machine cost, labor cost, and more. PADT and Stratasys have an ROI calculator we use to evaluate each CAD model. So here are 3 examples and the results. The first part in this extremely simple bracket has 7 through holes. It is basically 0.15 inches thick with overall dimensions of 1.65 by 3¼ by 1½ inches. I found I could fit 4 of them on the build plate in one Origin job. And if printed in the ABS-like resin, Somos WeatherX 100, would take 2 hours and 47 minutes to print these 4 copies. Each one uses 28 grams of resin. But how does that data fit into the full production cost? And what about other production methods? Let's compare this to using aluminum sheet metal stock, also 0.15 inches thick, set up on press brake equipment. In both cases, the desired annual production is 2,563 units. Note that this example assumes the Origin Two parts meet the structural requirements of the aluminum bracket. In some cases, the right choice of Origin Two polymer can indeed replace simple, lightly loaded bracketry. You might find it surprising that when comparing the 2 production methods, the break-even crossover point comes at just 12 units, as shown as the upper right of this chart, where the cost is $45 per part for sheet metal and $44 per part for the Origin resin version, meaning as soon as you get to the point of producing more than 12 parts, it's cheaper to 3D print even this simple part. Why is this? With the aluminum production, if outsourced, there is a fixed tooling setup charge that applies to any quantity from 1 onwards. For the full year's worth, the aluminum version clocks in at $11.25 a part, whereas the Origin version cost comes down to $2 a part. Even more noteworthy is the time to go from CAD to part. With metal forming, this is a 3-week process. With Origin DLP printing, the turnaround time is less than a day. So even for a very low quantity, if time is of the essence, 3D printing wins. Only if cost is more important than delivery time would you go with the sheet metal approach. Now here is a much more complex shape, but at the same time it is essentially a 2.5D model, meaning a vertical extrusion of a 2D drawing. With just one model fitting onto the build plate per print job, let's look at the production numbers using the same ROI calculator. Consider an annual demand quantity of 9,000 units. Here, the cost per part of Origin 3D printing in Henkel Loctite 3D 3843 resin is evaluated against injection molding with ABS. The break-even crossover point, where injection molding becomes the better choice, is not until 4,000 parts have been produced. A key consideration is the need to machine a mold. The injection molding approach requires a CAD to part time of 6 weeks, while the Origin DLP method yields a CAD to part time of less than a day. So there are several benefits to 3D printing under the 4,000 unit mark. Not only are the printed parts considerably less expensive due to mold costs, but in the 5¾ weeks while you were waiting to get the first molded part, you could have already printed 172 parts. Would this allow you to get to market faster and start establishing sales while continuing to print? Maybe this would be your bridge production route while waiting to receive the mold. Lastly, let's look at this camera mount used for in situ build monitoring. This geometry lends itself well to printing as a 3D array with 40 stacked parts per build, something that is easily accomplished on an Origin DLP printer using Stratasys GrabCAD Print Pro software. Here we note that the production requirement is just 1,000 units per year. Since the break-even crossover point doesn't happen until the 2,000 unit volume, it would take more than 2 years before injection molding becomes more attractive. In the meantime, not only is the cost per part for 3D printing only $17 versus $32 for an injection molded part, note the time difference. With the Origin 2 system generating 40 parts a day, you would already have produced the required annual production quantity in 5 weeks, freeing up the printer for other jobs, while the mold wouldn't even have been delivered by then. In fact, it would take 2 years before injection molding would offer a more attractive option. I thought I'd add a comparison across the 3 examples that briefly highlights the role of in-house machine operations. Looking at the orange slice of the pie, Origin, machine costs, and maintenance, you can see the effect of annual part quantity between the first and second examples. Although for different geometries, the first example, needing 2,563 parts, shows machine operations take up about 35% of the total final part cost, while the part with the 9,000 unit quantity shows machine operations taking only about 15% due to amortization of the equipment over so many pieces. So for the smaller quantity, machine costs are the driver. For larger quantities, the material cost is the primary factor. The third example is a bit different. Because this Origin 2 build allows 40 parts to print in just one job, it takes a longer runtime and therefore generates fewer turnarounds in a day. That plays into the machine operation costs being a larger proportion of the breakout, even though the influence of the material stands at 50%. With that many parts per build, the labor, shown in green, also has less of an impact. I think you can see that model geometry is only one factor in calculating overall ROI for a given part. Cost per part is always more than just material costs. For machining metal, there is a setup cost that applies every time parts are ordered from a third party, especially when ordering batches, say monthly, or across multiple suppliers. For injection molding, there is mold production and delivery time, as many molds are produced overseas. At the same time, 3D printing part production requires loading resin, removing parts from the printer, removing any supports from the parts, and cleaning and UV curing the parts in batches. Of course, all production methods include labor costs, whether hourly or overhead, as well as equipment depreciation and energy consumption. Secondly, often overlooked is the time to part, or here we say CAD to part. How long before the first actual part is completed? And what is the opportunity cost of waiting if you compare one-day production to delivery times of weeks or months before first part? Lastly, how many parts can you make simultaneously? A press break is usually part of a sequential production line, although production speed may be very fast. Injection molds may be designed with a sprue holding multiple parts, but this is also very geometry dependent, and the cost goes up if you need to add one or more sliders to produce undercuts. With the 14-inch height of an Origin 2 3D printer, you may be able to stack parts that not only increase the throughput, but allow printing overnight for unattended second shift production. Note that the cost sensitivity of each part can vary based on how many parts can be batched in a machine and the total production quantity demanded. Overall, the larger the quantity, the more parts that can be amortized over the capital expense of the machine. PADT would be happy to help assess the ROI for any of your company's parts. Reach out to PADT for more information about Stratasys Origin 2 systems and evaluating a project for 3D printing possibilities. We are an engineering services company founded in 1994, and we provide simulation, product development, and 3D printing services, as well as selling and supporting Stratasys, Ansys, Flownex, Geomagic, and Zeiss products. I hope you felt your time was well spent in learning about the Stratasys Origin Two DLP 3D printing systems. Check out the Stratasys YouTube channel for our other Origin 2 videos, and feel free to call or email us with questions about any topic we've covered, from materials and system operation to applications and ROI considerations. Thanks for watching.